Here's our last flip lesson for Unit 8. Our vectors, and this time it's this funny thing called cross product. Okay, cross product, dot product. These are two new operations that we've had with vectors that we don't have with other things. It's very practical, and our job here is to take the cross product of two vectors. And what this does is it creates a third vector that is orthogonal, or 90-degree angle, to both the initial vectors. If you go ahead and make like a gun with your hand, and leave your middle finger pointed sideways, your pointer finger pointed straight, and your thumb pointed up, that's what you do. If you took your regular fingers and you found the cross product of them, you would get the thumb. It would give you another vector. And there's more than one application for this. There's some geometric applications for this cross product thing. We'll talk about that in a minute or a few minutes, with the area of the rectangle formed by two vectors. There's also the issue of torque with physics, this twisting action, like loosening a lug nut or a bolt. And then magnetic and electrical fields, because those occur at right angles to each other, and we want to know which direction the electrons are flowing if we've got electromagnet. So it does have lots of applications, and those of you who are going to go into physics and engineering and whatnot, you're definitely going to want to know about those. And so there'll be a bonus video at the end that you can watch about the right hand rule, and you can look at some other ones about introductions to magnetism or electrical currents. Anyway, the book only gives us one of the ways to do it. Okay, I'm going to show you the other one that I think is intuitive, and you'll see the connection between it and the dot product. And the first one is, if you look at page 519 in the key concepts, it uses a determinant form for a 3x3 matrix to show you how the cross product is carried out. Now, that is kind of cumbersome, or it's not as intuitive. Like, why in the world am I using a 3x3 matrix for this? Yeah, but that's because we're in component form. The component form just gives us a bunch of right angles anyway, and it's hard to visualize kind of with component form. It's easier to visualize if you had a 3D vector and you had a radius and you had a direction. But that's how it is. But here's the alternate one. Check this out. This is vector A cross product B, or I'll say A cross B, is equal to the magnitude of A times the magnitude of B times the sine of the angle. And that should look kind of familiar, because dot product was just magnitude of A, magnitude of B times the cosine of the angle. But dot products give you a scalar quantity, and these give you another vector. So there's a little bit of a difference between the two of them. Oh, I hope I get this right. Yeah, okay. So this is what the key concept looks like here in your textbook, and it shows you that you have the I, J, and K directions here for unit vectors, and if you do the long way of doing the determinants there, you get these like subdeterminants. Boom, boom, boom. But if you follow this rule and make those little subdeterminants, where if it's I, you cross off everything in the I column and row, and you're left with this little matrix down here, and then the J column and row and the K column and row get crossed off, and what's left is the determinant that you used. Boom, 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 to get this kind of form. And I use the little hats on these things to tell you that I'm working with a vector, or that they're a unit vector there. And maybe you've never seen that before, but that's the way some engineers will do it. So we're going to look at example 3 kind of in both ways, the book way and kind of, I think, the more intuitive way, and it depends on what you're looking for as to which one you would use. But here's what example 3 looks like in normal form. They give us these two vectors u and v, and there's their dimensions, 3 by -2 by 1, -3 by 3 by 1. And they also ask us to show that the cross product, the new vector that we get that comes out the screen at you, is orthogonal. It's at a right angle to both u and v, which by definition that's what a cross product is, but we want to show that. So we plug the numbers in into our little determinant here, work out the math, Remember, hit pause or whatever if you want to just stare at it. I get negative 5i minus 6j plus 3k. If I want to put that in component form, I get negative 5, negative 6, and 3. So here it is. It's the dot product, or the cross product, and then dot product u. And if we get 0, then it's orthogonal. We take this answer here in component form, that's u cross v, and we take the u vector, 3, negative 2, 1, we plunk it there, and we do the dot product now. The dot product was just negative 5 times 3, 15, negative 6 times negative 2, which is 12, and 3 times 1 is 3. Add all that together, negative 15 plus 12 plus 3 equals 0. Okay, so we know that the cross product is orthogonal to vector u. Now let's go to vector v. And we find the same thing, use dot cross product, negative 5, negative 6, and 3. And we're going to dot product that with vector v, with negative 3, 3, and 1. So we get negative 5 times negative 3 plus negative 6 times 3 plus 3 times 1. And again, we get 0, and that shows that both of our original vectors are orthogonal to our new one called the dot product. Okay, that's kind of the haps behind that one. Now I'll show you alternate version on that one, and I think you'll see what's going on with this one. Okay, alternate version here. Take the same two vectors, and this time I have to find out what the angle is between these two vectors, because when I get to my new definition of the dot product or cross product, then it involves the angle, right? Okay, so what I need to do here is I use our other definition for the dot product, and I'm going to solve it for angle. So first thing I want to do is I want to find the dot product. Okay, no problem. U dot v in 3 dimensions, 3 times negative 3, and negative 2 times 3, and 1 times 1. We did that in the last lesson, right? So we get negative 14 for the dot product. Then we find the magnitudes, because we have to find those out down here. The magnitude of u is each of its parts squared, and then we take the square root of that. So 3 squared and negative 2 squared and 1 squared equals 9 plus 4 plus 1, or the square root of 14. I'm going to leave it like that. And then here's our magnitude for the other vector, is square root of 19. So dot product over the magnitudes, I take the inverse cosine. I didn't write that in there, but I need to take the inverse cosine of this right here, and again, angle of about 149.1 degrees. So now I've got that, and I can go over to my other definition, the cross product definition, that uses the sine of the angle. I've already determined what the magnitudes of those two vectors are, root 14 and root 19, and now we take the sine of the angle, and we get 8.3666 units. Now the book answer for the cross product was in component form. But if I found out what the magnitude of that new vector is in component form and changed it, just figured out how long that is, there we go. Negative 5 squared plus negative 6 squared plus 3 squared equals square root of 70, which is 8.3666. So this gives me the magnitude of that in one fell swoop. The component form gives you an idea of the direction, because you can take your straws out and you can look at them. You can think, oh yeah, that is a 90 degree from both of the other two. Unless you got a 3D program, that'd be pretty sweet. But this one, alternate version, tells you how big it is, and it does it super fast. And that's useful for real-life problems like we have in example number 4, which I'm going to use to just describe how this works in the real world. So you flip over really quickly to number 4. We're not going to do number 4 types of problems. We do that kind of thing in physics. But let me just set this up for you. We have that you're going to be trying to turn this wrench here. And here's you know how long the wrench is. You're pushing down with a force of 25 newtons on the wrench. You're always going to be pushing like a 90-degree angle, or oftentimes you are, because that's how you're going to get the most torque, the most twist out of it. Yeah. So what I've done here is I've just taken this vector here and I moved it over and made it so that it's like they're both originating from the same point, the radius and force vector. Now in the problem it says that the angle up here was 40, but if I drop this sucker down here, that makes this angle 50 degrees. 50, because 40 and 50 makes that 90-degree angle. And question with this kind of thing is it going to tighten or is it going to loosen the bolt? The formula for torque is the radius times force times the sine of the angle between those two vectors. That's how we would do the cross product. Okay? And so if we plunk these suckers in and we do the math, then we're going to find out if it's going to loosen it or if it's going to tighten it. We're going to find out which direction we're pushing the thing. Obviously, you can figure out which way the wrench is going to go around and what should happen, but we'll demonstrate that with the math. So here's the math. Okay, torque equals our radius is 0.5 meters, our force was 25 newtons, and the angle between them, sine of 50 degrees, and that gives me a value of torque of 9.576 Newton meters, and this ends up being in the positive y direction. You can kind of see that with the math in the book, except they get a 9.5 and they just drop it at that, and that's because they didn't they rounded off when they did this whole sine of 50-degree thing. But the only vector in their component form in the book is in the y direction. 0, 9.5, and 0, or it should be 9.576. Now let me show you a picture of what this would look like. And if you take your right hand, go ahead, take your right hand, and I'll show you what this might look like. Here's that problem again. I kind of drew in a yucky looking wrench, and then if you take your pointer finger and you point that in the direction of the radius, and then you take your middle finger and you point it in the direction of the force, which way is your thumb going? Which way is the only way your thumb can go? Towards you or away from you? Well, if you're doing it right, this is what your hand should look like. Pointer finger along the wrench, middle finger along the force, and the thumb is coming out at you. Or if you want to see it kind of more flatwise, there we go. The bolt is going to unscrew and come up out of the page. And again, the rule was for this thing, lefty-loosey, righty-tighty. So we're going to turn the thing in an anti or counterclockwise direction, and that's going to cause the bolt to come out toward you. And if we did the right-hand rule the other way and we tried to tighten it, our thumb would point away from us. So that's a pretty nice little deal, and I already told you it deals the same way with magnetic and electrical fields for the physics students. Okay, moving on, geometric applications for the cross product. If you take the cross product of two vectors, you get the number for your cross product is the value of the area that is formed when you make a parallelogram out of those two vectors. Let me demonstrate with a little picture here. If we got a vector u and vector v, and then we enclose that in an area, we fill in the space there between them. The answer that you get for the cross product is that area that's on the inside. So, man, it's really simple math. You don't have to have things at right angles. You don't have to drop down a vertical here and to find the height to multiply by the base. You can just do the cross product and you get the full area under there. And this is a slanty parallelogram, right? And any parallelogram, you can do this type of process. You get the magnitude of the cross product. It's the area that's in there, the bound section here of u and v. Now this is pretty cool because that paper right there looks flat, but what if it was tilted forward, backward, left, right? And you've got not just a two-dimensional thing, but two-dimensional sheet or area in a three-dimensional plane. So cross product is going to help you with that. You don't have to flatten everything out in order to do the math. So if you look at guided practice, maybe you should pause and take a look at example 5 and look over it, and then I'll work you through guided practice 5 on the screen here. Okay, so go ahead and hit pause. look at example 5, see if you can follow the math, and then follow along with me as I go through this math. So guided practice will look like those ones. We've got two vectors in unit vector form with the I, J's, and K's. Unit vector U and vector V, and we want to find out what the area is of the section bound by those two. So we take the cross product, and we're going to follow the same way that we did it back in example 3 with I, J's, and K's up there. And so we take the determinant and follow that rule, and we'll get, for this first determinant, that's negative 11, so we got negative 2 minus 9, and then here we got minus, we got negative 6 times 1 is negative 6, minus 12 gives us that 18 because it's minus negative 18. And on this one we get negative 18 minus negative 8, or we get 10. So we're going to write in unit vector form negative 11i plus 18j plus 10k, or if we want to put it in component form, negative 18, negative 11, 18, and 10. So we want to find out how big that is, okay? We want to find out the magnitude of that. We can take it in component form and find out the magnitude of the cross product. So we take negative 11 squared and 18 squared and 10 squared and take the square root of that. That's the square root of 545, which comes out to 23.345 square units. If you did this on a piece of paper and you found out what the height was, and you did the whole thing like you did in geometry, you would get about 23.345 square units. And you're going to want to trust me on that, but that's the way that one would work. So you got an example there in the book. You've got one here. You can go back over, but that's it. You get the numbers just like that, and you've got the area of that section. And then here's our last geometric application. I promise this will be it. I know this is a long one, and I'm talking fast. And I'll just talk fast. So let's say you've got your three vectors. You've got the original two vectors and the cross product. That'd be three vectors, right? And the cross product is 90 degrees from both of the other two vectors. So now you got three vectors, and they're all in different planes, but they share the same initial point, which would be three edges of a parallelepiped, or a three-dimensional, thing here. All right, it's a pencil box, whatever. So just like we did the area using the cross product, now we use the cross product and the dot product together to find the volume of an object like this. If we knew what the length of the edges were, if they were represented as vectors, we could find out the whole vector space, three-dimensional. So the concept here is triple scalar product. Look how easy this is. Okay, if you're given three vectors and they put them in IJK form, and so we've got vector T, U, and V. If you do cross product with two of them, and dot product then with that answer and the third one, it makes this. Remember, we could have done this with like the I, J, and K here, and then multiplied it, done the dot product later. But this way you could throw it all in there into one big equation. We take the determinant of the first vector, second vector, third vector in the first, second, and third rows. And we'll get ourselves the area of that three-dimensional object. Okay, so example 6 looks like this. You take T, U, and V and turn it into just the standard component form, plunk it into the determinant of a matrix. 4, -2, -2 for the T vector. For the U vector, we got 2, 4, -3, and for the V vector, we've got 1, -5, and 3. And at that point, you just type it in. Ask your calculator for the determinant, and you get 34. If you want to do it the long way, feel free to go ahead and do cross product, get an answer, and then do dot product with that, but you're going to get 34 units. I done it the long way, okay? Just for fun, because I'm like that. Here's guided practice. I already threw in the numbers because, what's the point of typing all that stuff out? Okay, I just want to put in, what are the vectors there? T, U and V. Okay, so there's T, there's U, and there's V, and I do the determinant of that matrix, and I get 86 cubic units. And there you go. So our engineering folks, you're going to want to look at the right-hand rule, and then if you're curious still, you want to see kind of an explanation of the difference between the dot product and the cross product kind of practically or more intuitively, you can watch the other link that's in the description below. Okay, I hope that was somewhat helpful. I'm sorry this was a long one, but it's the last lesson of the unit, so, suck it up. All right, we'll see you in class.